Hello everyone. I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics of Aligarh Muslim University. In our previous classes, we were having discussions on Anova and how it is similar to regression and how it is also different from regression. We have seen one of the uses of Anova that if we are increasing variables into the system, that the newly added variable, whether its coefficient is significant or not, we can test it through the help of Anova. In the present class, we will take another application of Anova, which is popularly known as Chow test. Now, Chow test is used when you want to compare two series and you want to see the difference. Like we take an example, suppose we want to study the relationship between consumption and income, and we have a series, a period from 1981 to 1990. And all of us know that reforms happened in 1991. So we can take another period which is after 1991, from 1991 to 2000. So we have two sets of series. One is for the period 1980 to 1990 and the other is one from 1991 to 2000. So using these two series, we can estimate two different functions. Also, we can combine this x1 and x2 and y1 and y2 in a series, and also we will be doing estimating another function. Now let us take a case. Like in the first one, this one is the case where we have pooled both of them. We have pooled both the first time period and the second time period. We get the value of intercept, we get 111.18, we get the value of B 5.58, we get the value of R square, that is equal to 0.70, that is 70%, you can say, and the errors summation E square in terms of the pooled regression. Using pooled regression means we have taken both the data sets together and the degrees of freedom is equal to 80. The same thing we also estimated for just for the first sample. It was from the first sample was for the period the first 1981 to 1990. 1981 to 1990. This is the first period. We have our intercept is 44, your slope is 12, and then we have my R square is 0.73, and we have our error, summation error is E square is equal to 3 this will be square over there, please note this correction, 3240. Same thing we do it for the second sample 1991 to 2000, means we are talking about this sample 1991 to 2000. We do it, so we get the value of y hat, the intercept term is 186, the slope coefficient is 2.8, R square is equal to 0.69, and this error square is equal to 3250 at these degrees of freedom. Now we can add, this is a correction, please note this correction, summation E1 square and summation E2 square. Summation E1 square 3240 and 3520. 3240 and 3520 is equal to 6760. And this is at these degrees of freedom n1 plus n2 minus 2k. So that is equal to 16. For the pooled regression, and now the next time what we will do, we will take the error from the pooled plus these two. So these two we write over here, and this is the error from the pooled term, that is 24379. So what we write, 24379 minus these, the error of the first equation, the sum of the error squared summation of the first equation and the second equation, 3240. So we get a value 17619. So we write it over here, 17619. Now here the F ratio is given by the formula, that is, you take in the numerator this one where we have summation E square of the pooled minus, within bracket, summation E square of the first sample plus summation E square of the second sample divided by K. And in the down what we can do, that is, we take summation E1 square, that is, summation E1 square is the summation of the first variable error. Summation E1 square is the error of the sum of the errors of the first sample plus sum of the errors of the second sample divided by N1 plus N2 minus 2K. So the same thing, we ignore this at the moment. Now, so that we can write 17619.66 divided by, that is K, that is 2. There are 2 samples, and down it is 6760, that is the error of the both the terms, divided by 16. 16 is N1 plus N2 minus 2K, that is equal to 16. Now we get the value of F ratio as equal to 20.85. So this is how we use it for Chow test. We use the F statistics over here. Now, so the null hypothesis is there is no difference between the coefficients of the two periods, and the alternate, there is a difference between the coefficient of two periods. What we do, we compare the F statistics. Here the V1 is equal to K and V2, because these things we need when we see the statistical table. And what is the basic rule? If F statistics is greater than F table value, H naught is accepted. H naught is not accepted, which means the population from where the samples are being taken are different. And if your F calculated value is less than F table value, then my H naught is accepted, meaning thereby the population from where the samples are taken are similar. So if F calculated value is greater than the table value, H naught is rejected. It implies that the two functions, 1980 to 1990 and 1991 to 2000, the two functions denote different relationships. The nature of the relationship between these two periods are different. That is, the relationship is changing from the first period to the second period. So using our F test, we can compare two periods, and this is this is in the domain of Chow test, and this was the demonstration of it. We will like to do one more application of this F test, and that is, we will check what happens when we are increasing the sample size. Now, this is used to check whether the estimates remain same over time or not. This helps to test whether the estimates change with the increase in sample size. Through this, we can check whether the estimate functions good outside the sample of data or not. So, we take a case where this is the original sample of say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of 16 observations. And then we will augment this with another 4 observations. So here the null hypothesis is there is no difference between the coefficient of the original sample and the augmented sample. Augmented sample means we will add these here only. 270, 270, 290, 290, and here 30, 30, 30, 30. We will augmented means when we had taken 20, this is augmented, and original is your 16. So we will check whether what is the alternate hypothesis, that there is a significant difference between the coefficients of the original and augmented sample. So we do the calculation of regression from the augmented sample. The intercept is 111.18 and it is 5.58 is the slope coefficient. Then the errors of summation errors, the square of the errors of the augmented is equal to summation y square minus y hat square, that is equal to, if we calculate, this is be 24379.66. and then so here that is, we are denoting it by letter A stands for augmented, and there will be denoting by letter O is for original, and this is done at the degrees of freedom n1 plus n2 minus k. Second, from the original sample means only 16 observations, where we have not taken the additional 4 more observations. So from those, that is the original sample, we calculate the value of y hat. The intercept term is 112.716 and the slope coefficient is 5.39. So the summation error squares of the original sample is equal to summation y hat original y square minus summation y hat square. So this is equal to 23953.43, and this is at these degrees of freedom. This calculations we can do it in we can do it by hand by using the method of regression, or you can simply do it by using Excel or any other software. Now, the third thing which we calculate is what is the difference between the errors of the augmented sample and the errors and the square of it of then the summation of it of the original samples. So we have this one and this one. So what we write, 24379.66 minus 23953.43. This is equal to 426.22, and the degrees of freedom we use at different degrees of freedom, that is n1 plus n2 minus k minus n1 minus k, and that is equal to n2 degrees of freedom. When we open the bracket, n1 cancels, k cancels, so what is left is n2 degrees of freedom. Now your F statistics is equal to the sum of the error, the square of the sum of the error of the augmented sample minus sum of the squared error of the original sample divided by n2, this whole divided by sum of the square errors of the original sample divided by n1 minus k. So that is equal to 426.22, and what was the n2? There were four items, so we write divided by 4, and here it is 23953.43, and what is divided by n1? How many items were there? 16. In the original sample there were 16 items minus, so in the denominator we have summation E square of the original sample divided by n1 minus k. So that is equal to 23953.43 divided by 14. So when we solve for this, that becomes 106.537 divided by 1710.959. So that is equal to 0.06227. Most probably in this case, because in this case this value will fall somewhere over here, it will not fall in this significant region. So if my F calculated value is less than the F table value, we accept the null hypothesis. So in this case, if we accept the null hypothesis, then what is the implication of it? We can say that there is no significant difference between the coefficients of the original sample and the augmented sample. With this, we come to an end of our discussion on analysis of variance. We started this analysis of variance by demonstrating it as a purely statistical concept. Then we have seen how the total variation can be divided into explained variation and unexplained variation. We have used, we have seen what are the differences between analysis of variance and regression. Then we have tried to interpret the Anova table, which is normally reported with the softwares giving the output of regression. Then we have moved to the next case where we are increasing one variable and checking what difference it is making on the analysis of variance, and based on that we are making a decision whether this newly added variable is significant or not. Then we added one more variable, and in our case we found that when we added that one more variable, it was not significantly contributing to the model. Apart from this, we can use this to check the difference between two different series in the purview of chow test. We are using F ratio over there also to see whether there is significant difference between two functions of different time periods. And finally, we saw a case that when we are augmenting the sample, is it making a difference in the estimates of the model? Meaning thereby, is are my parameters changing or they are still same? This is very useful in case when we want to check the stability of your estimates and see whether that function, means that sample, the interpretation from that sample can be applied for out of the sample also or not. We had a detailed discussion on analysis of variance, and I hope that the lecture was clear to you. With this, I call to an end for this lecture. Thank you.